Can Thevenin's theorem simplify reactive AC circuits? Imagine trying to understand a complicated circuit with lots of resistors, capacitors, and inductors. It can be tough to see what's really happening at the load. That's where Thevenin's theorem comes in. It helps turn that complex network into a simple equivalent. But when it comes to circuits with reactive components like capacitors and inductors, does it still work? The answer is yes, and it's quite powerful for AC circuits. In electrical engineering, especially in circuit theory, we often analyze circuits with alternating current. These circuits include resistors, which oppose current directly, and reactive elements like inductors and capacitors, which oppose changes in current and voltage. These reactive components introduce reactance, which depends on the frequency of the AC signal. Reactance is represented by complex impedance, combining resistance and reactance into a single number with both magnitude and phase. Thevenin's theorem states that any linear circuit with sources and impedance can be simplified to a single voltage source in series with a single impedance. This applies to AC circuits as well because the theorem works with complex impedances. To do this, we find the Thevenin voltage, which is the open circuit voltage at the load terminals, considering the phase shifts caused by reactive elements. Then, we find the Thevenin impedance by replacing all independent sources with their internal impedances. Voltage sources become short circuits, and current sources become open circuits, while keeping reactive components in place. The result is a complex impedance that combines resistance and reactance, giving us a simplified model. Once we have this Thevenin equivalent, analyzing the circuit becomes much easier. Instead of dealing with a tangled network, we just look at a single voltage source and a single impedance in series with the load. This makes calculating current, voltage, and power straightforward, even when the circuit contains reactive elements. It is especially helpful when the load varies or when designing filters and amplifiers, where frequency response matters a lot. However, keep in mind that Thevenin's theorem only applies to linear circuits. Nonlinear components like diodes or transistors are not suitable for this simplification. Also, while the Thevenin equivalent accurately models voltage and current at the load, it doesn't show how power is distributed inside the network. In summary, Thevenin's theorem can definitely simplify reactive AC circuits by reducing complex networks into a single voltage source and a complex impedance. This makes analyzing and designing AC systems much easier, especially when dealing with frequency-dependent reactance. It's a versatile tool that helps electrical engineers understand and work with complex circuits more efficiently.